Today what I want to do is spend some more time, a little more time with the law of sines and cosines, a little more practice there, and you're essentially just solving a triangle where you might know three or four of the parts of a triangle and you need to find out what the other components are. So we'll work on that, but then I also want to get into something, a very important area of application called oscillators or harmonic models, harmonic motion, simple harmonic motion, that kind of thing. We can use different names for that. So we'll start by solving some oblique triangles in segment 1. Then we'll do some simple harmonic motion type of stuff. And there's nothing really new here, just to sort of give you a flavor of how you actually apply it. So there's nothing really new in this second section, just maybe a little new vocabulary. And then what do you do when you start adding or maybe even multiplying functions together? So, and to see what happens when you take a trig function and multiply it something out by something else, or maybe add some trig functions together. So that's what we'll be covering today. So let's start with the oblique triangle stuff again. In the last session, we did this problem. Gave you two legs, 26 inches, 13 inches next to it, adjacent to it, and then an angle between them given to us at 40 degrees. And then these are the answers that we ended up getting when we did that problem in the last session. However, those answers, if you look at this picture, I tried to draw it somewhat to scale, and it looks pretty accurate with 40 degrees here and this 13, looks like it's pretty close to half of that. But you look at these angles in here compared to what we actually calculated, and they don't feel right, do they? They don't feel right. So that's where we left off in the last session. So in the interest of checking, I want to check this and see if indeed this is correct. So what we did is, since we labeled this angle C over here, then that means this length right here is going to be capital C. And then what did we label previously this angle in your notes? A. So this was angle A, and that means this side down here would be little a. And then that means this would have to be angle B, and this would be side B over here. Okay, so how could we sort of check without just going back and redoing all the calculations? We have two laws available, law of sines, law of cosines. Right? So we could just grab either one of those laws and go ahead and see if they work. Now, let's use the law maybe differently than the way we did when we worked this problem previously. So let's say I want to use the law of sines related to angle B, and then we'll pick one of the other angles also. So if we said, remember the law of sines? Yeah. The sine of an angle is to its opposite side as a ratio, and that's equal to that same type of ratio for any other angle and opposite side that's exist in this triangle. So let's check, let's put a question mark over this equal sign, because we're going to apply the law even though we know all 6 parts of this triangle, the 3 angles and the 3 sides, based on the work we did. You make that a small c, and this a capital C over here. So let's use our angle A. Let's see if that sine ratio of sine of angle A is to its opposite side, if that's the same. And let's check, why don't we check it at the same time with the third one? See what we get when we crank those ratios out. So this is a quick way that you can sort of check and see if you did your work right. My scale drawing, as I said earlier, doesn't look like it's right. So I was concerned, and we certainly don't want to have that on a recording with a bunch of garbage there. Okay, so let's check this out. So the sine of B, so we're going to take the sine of 72.5 degrees and divide that by its opposite side length, 13 inches. And is that, I'll keep a question mark over the equal sign, is that going to be the same as the sine of our angle A, 67.5, and these are going to be approximately equal because I'm rounding off the measurement of these angles and the side length as well. and angle A's opposite side was the exact 26 inches. And then we have the sine of C, which is 40 degrees, is to its opposite side 18.1 inches. Okay. So with those three values up on the board, all I'm going to do is take my calculator now and make sure I'm in the correct mode, degree mode, and degree measure here. And we're just going to punch this up. So we're going to take the sine of our 72.5 degrees, close that angle, divide it by its side opposite length, 13, and we get a number. And then we're going to compare that to the sine of 67.5 degrees divided by its opposite side, 26. Aha. Okay. So do you see how that sketch we drew, that approximate kind of eyeballed sketch, and then we did all of our fancy calculations, and it looks like something's wrong. Okay? And then let's go ahead and get the third one just to see if we can detect where our error might be. Of course, remember, I don't know if you remember, but we used our 40-degree angle. We found I think we found a side length, another side length, and then we went and used the law of sines and worked our way into it. So what happens if you made a mistake somewhere early on in the solution problem, then it's going to end up manifesting itself in the later work. So let's take that last one, sine of 40 degrees.
We should have known because we guessed on the angles, and then we're like, whoa, we were way off.
Yeah, exactly, but I ran out of time.
Right.
So, aha, look at that. So where do you think the error might lie? Look at these results on the calculator. Look at the results on the calculator. It appears like the error may exist up in here, right? But the 13 was known. So it appears that possibly the 72.5-degree angle would be wrong. Okay. So this is the kind of thing, this is actually useful. You know, instructors making mistakes like this is sometimes, of course you guys are responsible also because you didn't catch my mistake. Okay. I'll pass the buck a little bit. But anyway, this is how you take a scaled drawing, and this is the kind of thing you want to do, is always have some backup means of checking yourself instead of waiting until you get your paper back. Okay. So let's check this 72.5 degree measurement, which was which angle? That was our angle B. Okay. So let's go back to the original problem then, because we knew the little b was 13 inches. We knew that angle C was given to us as 40 degrees, and we knew side A was 26 inches. So that was our given information. And so with those three pieces, once again, I'll draw it. 40 degrees, 13 here, and 26 there. And we're trying to figure out this angle down over here, angle B. Can we go straight to angle B? Can we go straight after angle B using our laws or not? You can't use law of sines right away. Here's why. Look at the law of sines. The law of sines, you have to know 3 of the 4 pieces. You have to know 3 of the 4 pieces sitting here, which means for sure you're going to have to know a pair. You're going to have to know an angle and an opposite side. I mentioned that last time. And you have to know an angle and opposite side to be able to use law of sines. And you can look right here at the given information. We don't know an angle and an opposite side. True? Okay. So we cannot use law of sines to get started on the problem. Now, as we did the other day, we went ahead and used the law of cosines, didn't we? We used the law of cosines because law of cosines allows us to use where the emphasis is on the sides. Notice what we have here in the original problem, side, angle, side. If you work your way around the triangle, we have a side, angle, side condition. The given information's emphasis is on given side length. So usually that's a clue to use law of cosines. So let's just redo the problem that we did the other day. So what do you think you have to do without looking back at your notes? Is it David or in the middle?
Me?
Yeah.
Jason.
Jason, sorry.
You'll get one of these days. If I remember right, it's you use the side B. This is squared equal to side A.
Right. It's a Pythagorean. It's a.
Yeah.
You just take the sum of squares equals one of the legs, one of the sides squared, and then you have to make an adjustment to it. So.
Minus 2 both legs, cosine 40.
If I wrote the law of cosines, say this way, if I said b squared equals a squared plus c squared, then remember what you have to do. You have to subtract off twice the product of these sides times the cosine of this angle opposite this side. Now, if you look at that, what you know here is you know the A and the B, but you don't know side length C, or you don't know side angle B. So we can't use it in that form. Where you use the law of cosines, or when you use the law of cosines, typically what you're going to do is be solving for the angle, or excuse me, the side that is opposite the known angle. The side opposite the known angle. And you don't have to memorize all that. All you have to do is try it. You have to memorize the formula, but then see if you have enough information to actually use it. So what I'm going to do is I'm going to write it as c squared, and I believe this is what we did before. C squared is going to be equal to a squared plus b squared minus 2ab cosine of angle C. Then we're going to drop in our known information. We have our 26 squared plus 13 squared minus twice 26 times 13 times the cosine of our 40 degrees. And then all we have to do with our calculator, which I did the other day, is I build a big radical here and tuck all this information inside it. So all of that information, 26 squared plus 13 squared minus, that's essentially 26 times 26, but I'm just going to leave it as we see it. And then we'll get an approximate value. And I'm pretty confident that that value is going to be okay. Look what I'm doing. I'm hitting my shift key and my enter key to take me back through the memory. So here's where we had done previously the calculation on this. And what I'm going to do is I'm going to come back in here just to make sure I didn't make an arithmetic error somewhere. I'm going to come in here and change this to 26 squared. And I'm going to just, I know 169 is 13 squared, but just for safety, I'm going to put 13 squared there. And then right in here, I'm going to put, oh, I think I see an error.
Yeah, I was going to say, when it's 2, 13, 26, and isn't that like saying 2 times 13, which is 26, no. And 2 times 26, which is 52, which ends up being 26 times 52?
On the last part?
Where it says 2 and the 2 legs. So it's
right
like
here.
saying 2 times 26, which is 52, and 2 times 13, which is 26.
No, you don't distribute that.
Oh, you don't?
No. right? You only
I
use,
times 26 and 13 together and multiply it by 2.
yeah. So you get 26. You've now buried that 2 in with the 13 once you say that's 26 times that other 26. You don't distribute. A group of products don't distribute across. You know that. But anyway, I'm going to go ahead and do 2 times 13, or 26, I guess, 20, and I have to insert 26 times, right? Now it's okay, isn't it? Isn't it now exactly the way? Oh yes, I'm still inserting. I need to tuck a 13 in there. Okay, good. Now you folks are keeping tabs on me. Okay, good. Times the cosine 40, right? Okay, that value's okay. So that part of the calculation agrees with what we had the other day. So this is about 18.1 for that length, inches, for side C. Okay, next, so we then had 18.1 here. Everything's agreeing so far. Okay, then we now have a side length and its opposite angle, and now we can drop in and use law of sines. We can now drop in and use law of sines. So back up on the top of the board again, why don't we go ahead and work on trying to see if that 72.5-degree angle came out right up here. So I'm going to just drop back and redo this problem. And so we're going to be looking for angle B right here, and its opposite side, angle B, the sine of angle B divided by its opposite side, 13, and that's going to be equal to, I'm going to go ahead and use our 40 degrees here. Sine of C to its opposite side length, C. And sine of C, 40 degrees. Our opposite side length is now 18.1. And notice how I had previously stored that value in the calculator, rounded off here. So this is approximately equal. And so this implies that the sine of B then, by multiplying both sides of this by 13, is going to be about equal to 13 over the 18.1 times the sine of angle 40 degrees. What I would do right there is I would go ahead then and write angle B is going to be approximately equal to the inverse sine of this ratio we see here. So we're redoing, as I said, the calculation from the other day. So we're going to go inverse sine of 13 times our sine of 40 degrees divided by our value, which we have stored in the memory of the calculator under letter alpha C. So we go alpha C and close that parentheses. And this should be the value. I'm now going to store this reading, as you see with the calculator here. Where am I going to store it? Where do I want to put this in the memory? B. Angle B, alpha B. Ah, that's strange. Is that too small?
Just check it again.
27 degrees. Look at the picture.
Could be sine of 27.5.
Look at this picture.
13, whatever that is.
That doesn't look too bad, does it? This drawing is fairly accurate. Okay, 13, roughly half of 26. That angle looks fairly small. We'd gotten previously a 72 out of it, which didn't feel right. So the corrected value, it looks like, might be okay. So we pick up a 27.5 degrees for that reading. So that's probably where our error was previously.
I don't quite understand why we wrote B equals 180 degrees minus 40 degrees plus A sine A. That's
So
all.
what happens is we found angle A previously first. So let's go ahead. So I don't want to confuse people, but anyway, here's our new work right here. Okay, and this is all looking good. So let's now go and let's go ahead and recalculate the angle A using the law of sines. Right? So the sine of angle A is to its opposite side, which is our 26. Okay? And then what ratio would you probably want to use for the other? Huh?
Our known angle.
Our known angle. So the sine of 40 degrees to its opposite side, which we used previously, 18.1 approximately. And notice I start out writing my law with exactly equals, but once I drop in a calculated value like I have here, that's gonna be approximately equal in the work we do. So then multiplying both sides by 26 and taking the inverse sine of both sides, angle A will then be equal to the ratio of 26 to the 18.1 times that sine of 40 degrees for the angle A reading. And so actually what I can do is I can simply replay this expression. I can come back in here, inside here, and change this to a 26 sitting in the numerator. And then I can come down here and be storing this in memory cell alpha A. So all I have to do, if I have a similar expression, all I have to do is come back in and edit it. Jason?
Yeah, wouldn't you want where you have A is approximately equal to 26 down there? Shouldn't it be sine inverse first?
Boy, you guys are catching me today. Good. Thank you. So angle A is going to be approximately equal to the inverse sine of this. I did it correctly on the calculator. I just hadn't written it on the board properly. Thank you. And then we hit enter. 67.5 degrees.
We had that once.
Okay, so maybe the only error in our earlier work was right here. Was right here with this angle. So the angle A is still coming out to be this 67.5 degrees. So even though I haven't done a new problem with you, I've gone back and used both laws, sine and cosine, to sort of see if we could make an adjustment to the work we did previously. Yeah.
The sum of all those angles is 135 degrees.
Yeah, doesn't add up to 180.
Boy, I'm having a rough day, aren't I? Okay.
Staying up till midnight.
Christmas.
Yeah, I got to stop staying up till midnight watching the Olympics. Okay. Right. And so notice what he just said. He checked by adding these angles together. And so let's see, our new calculated value on B was 27.5 degrees. And then he did a spot check of 40, 27.5, 67, and we're not getting up there near 180 just by eyeballing it. Okay? Well, anyway, I know the laws. It's just I can't use them right. Okay? Now your objective is to go find my mistake. Don't.
Jesus.
Okay. Alyssa?
Should we be looking at, I might be completely off, but shouldn't B be somewhat close to half of A, the angles?
But B was good.
See,
That's what
this drawing I think is fairly accurate. This angle looks pretty good. These ratios of these side links look pretty good. That angle looks pretty close to 40. That angle looks like it should be beefed up. So something looks fishy here with this angle.
Is our results not an indication that that can't be a triangle with those links, is it? Is all the math done correctly and just those links won't work out as a triangle? Is that the...
Well,
is that
check
what
it
we're
out. As
finding
long as two of the legs added together add up to longer than the third leg, check this out. If you add these two legs together,
They're longer
that's
than
31 18.1, which is longer than this. So indeed, we do have a triangle. So can we redo? There's a problem. I think this is probably okay. I think there's a problem maybe in finding this angle A. Sine of A is to 26 as the sine of 40 is to its opposite side. That's set up properly with our law of sines. I'm not sure. Do I want to spend any more time on this? Let's spend one more moment. Let's take and use law of cosines and see what happens. Let's use this side length, which we knew. Let's use this calculated value, which was feeling pretty good based on the sketch. And then we have these other given pieces of information here that I've starred. Okay. If you just do the 180-degree rule, angle A should be what? So this is what we're questioning right here. This is our question mark right there, isn't it?
Should be 112.5.
Yeah, and so what you just did is we took angle A should be equal to 180 degrees minus the sum of 40 degrees and the 27.5 degrees, right? And what'd you say you got, Jason?
112.5.
I'm sorry.
112.5.
112.5. And if you look at the picture, that looks like it should be up a little 90 degrees or more, doesn't it? Yeah. And 112.5 degrees. Okay, so that looks like it probably should feel more correct. So let's see if we can use the law of cosines then to solve law of cosines to solve for an angle which we have not done yet. Law of cosines. Yes, Emily?
Before your calculator went blank, does it matter? It looked like you were plugging in capital C and not lower c. So were you plugging in the 40 degrees instead of the 18.1?
No, because I got the same answer and I did it manually. I didn't do the
Okay.
store.
Oh, okay. Yeah, you didn't do the store feature. Okay. So let's just, this is actually worth taking a minute or two on using the starred information up above. The reason is I want to find angle A using law of cosines, and I haven't shown you how to use that. It's pretty obvious what you need to do. So the law, if I want to use law of cosines to solve for angle A, I have to start with the opposite side. So I have to take this 26 squared, and that's got to be equal to the 13 squared plus the 18.1 squared, minus 2 times 13 times 18.1 times the cosine of the angle opposite the 26-inch length, which is the angle A that we were having trouble with. Everybody okay with the law? Now, the way I usually do this is this term is negative, right? This last term here is negative. So I imagine adding it to both sides of the equation to make it positive. So I bring it over to the other side of the equation through addition, and I end up with 2 times 13 times 18.1 cosine of the unknown angle, and that's going to be equal to, leave the 13 squared where it is, the 18.1 where it is, and bring the 26 back over to the other side. Do you see what we're doing? Working on isolating the cosine of the unknown angle, and then we'll take inverse cosine of both sides. Everybody with me on how you just play with these things until you finally get it right? And you could do a scaled drawing with a protractor and a straight edge with a rule and actually measure the values and be pretty darn accurate if you wanted to do it from geometry. So angle A is going to be equal to the inverse cosine of 13 squared plus 18.1 squared minus 26 squared over 2 times 13 times the 18.1.
Robert, where'd you get that 2 on the left-hand side?
Right here.
Don't you have to divide it?
Well, 2 times 13 times 18.1 times that cosine. That's all
Oh,
one.
I'm sorry,
that's-
you just like
that's-
shimmied the whole
Yeah,
thing.
that's all one
Okay.
term, and we're adding it to both sides to bring it over here.
I gotcha.
Okay. And these are all approximately equal because of the use of the 18.1 in there. All right. So we're hoping that this turns out to be 112.5 degrees. So we're going to take the inverse cosine. Now you have to be very careful here to make sure all this stuff, look, watch this inverse cosine expression. I need a new parentheses here to stick the numerator, all the arithmetic in the numerator. The 13 squared plus the 8, plus the, well, I can't remember. I'm just going to use 18.1 because I don't trust what I stored in the memory. And that's probably where I got in trouble previously. Yeah, by using the store and duplicating one of my letters. And then divide by, notice a new parentheses for the denominator. Be very careful there. 2 times 13 times the 18.1. And then that closes out the denominator, but then I need to close the inverse cosine and see what I get. There we go. Thank goodness. 112.4 degrees is an approximate answer there. And so now we finally fixed that mistake from earlier.
It's like you always say, do it first and then go to calculator.
That's it. Yep. Yep. And I've been doing this for years, so if I'm screwing it up, take the approach that I use to heart by drawing sketches to be able to catch mistakes. Okay, that's a long-winded segment. Let's go ahead and end this. We used law of sines and cosines numerous times, so that should have been a good practice session for you. Okay. Yes, Jason.